There's going to be a lot of little code snippets in here, and it's probably going to go down towards the bottom of the screen. So if anybody wants to see things, you might want to move where you can see the bottom of the screen for some of the code. I tried to move up things as high as I could, but some of this stuff, it might be a little bit better to get a little closer. And in the interest of time, because we're running a little bit late, at the end, I'll go through all the slides, and I'll take questions in the back of the room. So this way the next speaker could set up and we could catch up a little bit. So, and we got the bell going on. So one of the superpowers of Postgres, we talked a little bit about extensibility in some of the roundtable and throughout the conference. But one of the key ones early on was around procedural languages. Postgres has this unique ability to create language syntax. Postgres has many different languages. Most people use PL/PG/SQL, as they should, but there's many other languages like PL Perl, PL Python, PL V8 so for JavaScript. We're going to talk about PL Rust, which is a relatively newer procedural language. We're going to go deeper onto what a trusted procedural language is and how do we do that with a compiled language like Rust. Postgres has trusted and untrusted languages. It's not an indicator of whether or not that's the quality of the code. It really comes down to what access you could do out of those stored procedures. Can you write a procedure that does an RM-RF across your file system? Can you make network calls? Those are all untrusted things. So you have to be a super user to be able to use the untrusted languages. Trusted stays sandboxed inside of the database. So this way it can't do things out on the file system, can't do things on the network. It can't access directly Postgres internals. It has to go through different APIs. So this way it's protected. You're not going to be able to access shared buffers and access data that you couldn't normally see through your different security mechanisms. So it's really important when you're talking about writing code, using it in a trusted language, except for those few cases where you need it in order to be able to, say, make a network call for an untrusted language. And Rust makes that particularly difficult because it is a compiled language. It is, it's a new type of language that's kind of out there. We're going to see a lot of Rust code today. We're not going to do a Rust tutorial. The syntax is different and weird. So there's other ways to learn Rust, but you're going to see some aspects of it in there. But it gives you the low-level performance like C, but it gives you the memory management of some of the higher languages that are there. So this way you don't have like pointers pointing to random places. You don't have to worry about how you do garbage collection or any of these other things. Rust takes care of a lot of that stuff for you, which is great inside of a database. PL Rust is really accessing that Rust language inside of a procedural language. It's based on another open source project called PGRX. PGRX is a pretty novel extension on top of Postgres that creates a framework on top of Postgres internals that allows you to write things in Rust. So the PL Rust is written in Rust, allows you to write things in Rust. There's a lot of other extensions out there written in Rust using PGRX as the basis to be able to access Postgres internals. So a lot of the things that you build on top of PL Rust is based on that project and leverages PGRX to be able to get it there. So what happens when you create a PL Rust function? It's a little different than other procedural languages. It's compiled. So when you take that function just one, which returns the integer one, first thing it does is it writes to the catalog pgproc. So it's going to write it's going to get the OID, it's going to put the name in there, what the parameters are, what the return value is, and it's going to put the source in there. Right? Then it's going to run through the PL Rust validator. So all procedural language handlers have a handler and a validator for whether or not it needs to validate the code, either when it's at create time, or if it doesn't do it at create time, it has to do it at the first time it runs. So PL Rust, it's forced to go through the validator. It's not an option like other languages. And what the validator does, it takes the code, so in this case, OK sum1, and wraps that in some boilerplate and creates a file lib.rs. And then it creates a crate.toml file, right, which is equivalent in Rust, like a make file. So we're generating that Rust code, those Rust files that you need. It's then going to run through a number of lints. So it's going to statically analyze the code. Then it's going to run through the Rust compiler. So we're going to generate a compiled object. And then at the end, it's going to go ahead and update PGProc with the results that's in there. So what you get is, if you do a PG dump of that function, you actually get the binaries of that individual function. So you'll see that it's actually stored in a JSON format, right, which has the original source code, along with everything it needs in order to be able to execute that binary. So this way, it's not an interpreted language. You're actually running the binary itself as if it's just a .so file on your file system. So why is it in PGProc and not just stored in a file system? A few different reasons. One, we need to be able to store and persist that. We could store it in the file system, but the first time you run a PL Rust function, a create function, if you've never run it on that system before, it may take a couple minutes. Rust is not fast at compile time. A lot of the safety mechanisms for Rust all happen at compile time. So first time I tried PL Rust, I installed it on my laptop. It took 5 minutes to do that first create function. There's ways to speed that up with caching various different objects, but it takes a long time. The other one is, when you do that create function, how do you get it on all your replicas? If you have a file there, how are you going to get it so this way it's transactionally consistent in your replication stream and get it out of all your replicas, right? Along with your backups and other things. So you want it to be part of point-in-time recovery in your data directory, right, when you do backups and other things. But also, if you're going to do a PG dump and restore, if you have 100 PL Rust functions, you don't want it to take an hour in order to do a PG restore, just getting all your functions back. So storing that inside of really the source of there solves a lot of those problems. And also another thing was, could you create another table to store the binary instead of storing it in PGProc? And there's some race conditions around replace, to do a create or replace as you're executing it, that it just made it too difficult in order to free up the local sys caches and other caches while that's happening. So it just ended up being easier to put it inside of PGProc. So what makes PL Rust be trusted? It's a compiled library, right? Same thing as if you were writing it in C, right? So some of it is inherent in Rust. Like I said, at compile time, it does a lot more checks, right? It does a lot of things around memory and pointers and other things that prevent you from doing things that could be bad for the system. Another thing we do is, through a number of different things, it removes the ability to do a lot of unsafe things inside of PL Rust. If you were going to write the code yourself and not run it through PL Rust, there's a term called the unsafe inside of Rust that the compiler is just going to basically not do its normal checks. You're free to do whatever you need to inside of Rust to be able to do that, but you could end up, doing some things with pointers or other things that could cause problems. PL Rust, you can't do that with trusted Rust. Right? And the other key thing is there's a specialized standard library for PL Rust that locks down a bunch of other things like access. So the first thing is lints. When we're doing the static analysis of that, there's a number of lints that are there that checks for those things like unsafe, macros that might be unsafe. It's really cool that Rust has a macro that says include string that loads a file and loads it into a string. Right? So part of PL Rust is that's disallowed with those lints. So you can't just include etc password and have it as a string. Right? Those things are purposely blocked as part of PL Rust when you're running it as a trusted language. PostgreSTD is a standard library for PL Rust. So how Rust works, it has a standard library based on your operating system, whether it's Linux x86 or Windows or ARM. There's a specialized standard library just for Postgres. So it's like you're building your Rust code for the Postgres operating system, not necessarily Linux or ARM. And what that does is a few things. It replaces the standard sys libraries that are in there for all the system bindings, stubs out things that are inherently unsafe from a trusted language perception, and then other areas, it actually leverages Postgres internals. So around memory management, it uses Postgres' memory context for things like palloc. So this way, it's all part of the same memory context inside of Postgres. So you don't have memory leaks inside of your code. But if you're running it on, on your, self-managed instance, you may want to have Postgres as trusted, but you could run it as an untrusted language too. So there's various different configuration options if you want to, of things like workdir is where it puts those temporary files while it's being compiled. Allowed dependencies, what can you actually link to? And those compile lints. If you really want to run unsafe code, you could turn off those lints and be able to run full Rust inside of Postgres if you want to. So what does it look like? So it looks like a lot of cases, it does look like any other Postgres function. The wrapper itself looks the same. But how it interacts with the Rust code under the covers is a little bit different, right? Because when you want to return something, you don't necessarily just return just an integer or a string. It has to come back as a result option T, and that T being whatever your return value is. Right? So this way, Rust developers will know what that is, so this way you know whether or not you have to return back a null or not. It handles all that. But any PL Rust function needs a return value in that sort of format. Other things with parameters coming in, because your parameters can be null, the Rust code is very strict at compile time of being able to know whether or not it has to handle null or not. So Postgres has a syntax on its create function called strict. Strict tells Postgres whether or not the input parameters can be null or not. If a null value comes in this case on input, if it's null, Postgres, you define the function as strict, it never executes the actual function. It just returns null. So this way, you could just assume that the value will never be null for your code inside of there. However, if you don't put it as strict, your code has to handle the case if the input is null. So when that comes in as a parameter, PL Rust takes all your input parameters as options. So you need to be able to unwrap those in order to be able to get to the value or handle it if it is a null. Right? So subtle things that, like when you're thinking about coding in Rust, how it interacts and interplays with Postgres, you have to understand how it's being called, right, and how you return different things. There's a number of different data types. Postgres has many, many, many data types. Right? Some of them map very nicely to Rust data types. Like all the integer types all map to equivalent Rust ones. The text in varchar maps to strings. Right? Same thing with the floats and the doubles. But there's a number of things that are very Postgres specific, like JSON and JSONB, times, dates, even ranges. All of those leverage the things inside of PGRX that maps to those individual ones. So there's custom data types inside of PGRX that are exposed through PL Rust that allow you to use the Postgres data types inside of your Rust code. Some of them, like JSON, it leverages the crates SERDI. So this way, the SERDI JSON crates, so this way you could use your normal Rust code handling JSON. Others are brand new, like dates. So things like numeric. Numeric is a different type of database, data type inside of Postgres, right? Because it can handle 131,000 digits, huge numbers, right? So it's not equivalent to Oracle with a number data type, which has 38 digits. Right? It's much, much bigger. So it really maps to any numeric data type into PGRX. But a lot of times you could just use it as a regular number like we have here. And we'll see in some follow-on slides how numeric could be a little bit different. But for simple arithmetic operations, it works fine, like any other number type. But when you have something like a date, needing to be able to generate a data type for Postgres, it's a custom constructor there where you pass in the year, month, and date. Right? So how you work with them are a little bit different. You need to be able to leverage the stuff inside of PGRX in order to be able to know how your individual data types work with them. Can use composite types. So if you have a composite type like chords that has an X, Y, and Z component to it, it's mapped inside of PL Rust as a PG heap tuple structure. So this way you have getter and setters on each of the individual elements inside of that type. So this way you're able to access them or set individual things inside of there. So you can work with your normal data types that you may have created inside of PL Rust. Stored procedures, you need to be able to run queries. That's why you create a lot of them. There's some simplified macros over top of SPI. All of the stored procedural languages uses SPI in order to be able to access data inside of the database from your stored procedure code. PL Rust has some simplifying macros around that. One of them is the SPI get1 function. If you're just returning one value out of a SQL statement, you don't have to create a lot of other code. That macro there is just set up to return a single value. So we're just doing, select one from, Oracle, select one from Dual, right? Or just select one, you'll get that one back. But you can use full SPI. This way you could connect. You're not really connecting to the database, right? You're not creating another connection. It's just how SPI works. You're connecting in the context. But there you could do things like updating rows and create prepared queries and cursors and pretty much everything you need to do. You have full SPI access there. But again, this is a lower level language, so you're doing things like defining the data types. It's not going to interpret it for you. So as you're sending in values to that, you need to tell it that it's the OID of an int4. Right? And there's macros for that. But so you're being a little bit closer to C in some of these things in your interactions. But you're still doing it at a slightly higher level language. Logging, lots of times you're going to be doing your stored procedures. You need to log things, raise notices and other things. There's again, macros for that. So this way you could do log, notice, warning, error, bunch of other things. Or if you need to have full access to eReport inside of Postgres, that's available to you too. Right? So you can send up custom error codes as you're going along. But a lot of times the macros are more than enough. Right? They're very simple, very easy to use. But you get them as part of the Postgres logging. Again, part of the things that tie in directly to Postgres, your Rust code starts tying directly into the Postgres engine. This is kind of a novel thing inside of PL Rust that other procedural languages don't have. It's dynamic function calling. So a lot of times when you're writing code, inside, you have one stored function calling another stored function. Right? And going through SPI for that is pretty expensive operation. Basically, it then has to go through the parser and the planner and other things. PL Rust exposes the function call interface inside of Postgres internals. So you could have one function call another function without going through the parsing and planning steps. And that works for any function that's defined inside of Postgres, whether the built-in functions or anything that's added by an extension or anything that you create yourself. If you have one PL Rust function calling another one, PL Rust calling PL PGSQL, or anything like that, you could use the direct function call interface to bypass SPI in order to be able to call those things. Right? Because it's layering over PGRX, exposing the function call interface inside of Postgres was pretty straightforward for the PL Rust project to be able to do. So in this example, we're calling the soundX function directly. That's part of the fuzzy string match extension without having to call SPI in order to do it. Triggers. A lot of the code is written in triggers. Right? A lot of people, they might avoid stored procedures, but they add triggers for auditing and other things. You could write them also in PL Rust. It comes in as a trigger structure. that you could get the operation out of there. So in this case, it finds an insert. Otherwise, it defaults and throws an error. Then you could get the new and the old, depending on if it's an update, insert, update, or delete. Those come in as those PG tuple structures. So this way you can have the getters and setters on the individual things inside of there and manipulate the rows that are coming in, change the values if you need to, or just audit and insert it somewhere else. The Rust landscape, a lot of things are written using crates. There's a lot of additional functionality out there in the Rust ecosystem that allow users and developers to be able to get a lot more functionality in there. So you're able to use those crates inside of your PL Rust functions. So there's some additional syntax in there that allows you to create a block for your dependencies if you're going to use a crate. So in this case, the rand crate. And then inside of the code, you could use that directly. So this way you don't have to create all that or import it in. Right? That all comes in as part of the build step. So for trusted Rust, one of the things is you don't want to open it up to the world of being able to have any independent ones. So PL Rust has the ability to allow list certain crates that you could use in there, because it does run through the same build step as PL Rust when you pull in those crates, because it pulls in all the code, compiles everything together as a single shared library. So it's going to run it through all the lints. It's going to run it through and compile it against Postgres TD. So if some of those crates don't conform to what works there, that's going to fail. But a lot of the crates that are most frequently used allow you to build with no STD, so that a lot of that stuff just works. But there's a function in there called PL Rust allow dependencies. So from the SQL prompt, you could see what crates are available that you could use for your stored procedures development. And there's a config option that we mentioned earlier that allows you to add to that allow list. So if you want to be able to add additional ones, they're there. So one of the big reasons why you want to use PL Rust would be around performance. So HammerDB is one of the performance tools that people use in order to measure performance of an individual database, and it uses all stored procedures. One of the functions that it uses is dbms random in order to return a random number between a start and an end integer. Right? And this is basically the code. I kind of compressed it a little bit so it fits better on the screen. But it runs the internal random function and then truncates it, so this way it gives you that in a given range. So running that in PG SQL, I have to run it 1 million times in order to be able to get meaningful numbers, but it runs in about 620 milliseconds. Pretty good for running that 1 million times. So what if we did that and took that exact same thing but ran it through SPI with PL Rust? Right? So we take that as a select statement, run that same trunk random, right? Send in the values for the start int and end int, right? Running it that way, it's 14 seconds, not much faster, right? So it's actually significantly slower. SPI in PL Rust is not as efficient as PG SQL. PG SQL has a lot of optimizations that when you run it multiple times, it's going to cache the plan. PL Rust doesn't have that same cache plan. So as you're running multiple times inside of through SPI, that 1 million times, that same thing has to be parsed, planned, and then executed 1 million times, where PG SQL only had to do it once. So SPI inside of PL Rust, at least today, with the version that's out today, not very fast. So if you have your functions have a lot of SQL, it's probably better in PG SQL. Future improvement that the community wants to work on is improving that. It's a simple thing as far as caching those plans, but it's on the list of things that I saw the community working on. So what if we change it to the function call interface? So we're able to call the internal Postgres random function, right, and then use the internal Rust things to be able to truncate that and execute that. That's in 1.9 seconds. Still slower than what PLBG SQL was. You're doing a lot more context switching there, right, in order to be able to go through there, and there's a lot more code to go through compared to just executing it once in PLBG SQL. But you can see how much faster this is compared to the SPI aspect of it. So there's some performance improvements there. What happens if we do it as native Rust, just using the RAND crate? The RAND crate already has a gen range function on there, so we don't have to be able to do the trunk and all the other things, right? It just passes in the parameters directly to the crate and doing everything all in straight Rust. Now it's twice as fast, right? So when you could run everything all inside of Rust, you start seeing those performance improvements, right? So, depends on how you write that code. Same as any language. You could write very fast, efficient code, or you could write things that are slow. It doesn't matter on the language. It's a lot of times it's how you write it and leverage the language. But that's cool, right? It's running twice as fast for those million things. What if we try something a little different? Fibonacci. We all did this in school, right? It's a nice example. Notice here I have this as numeric instead of an integer. So I wanted to do really big Fibonacci's. Wanted to see what that might return. And then for Rust, using the num big int crate in order to be able to use those really big numbers, right? That allows you to have arbitrarily large size integers and you could work with them. Great for when you have really big numbers you want to work with. The numeric data type in Postgres, super slow, right? It's very precise, but super slow. Trying to leverage this here. So you have to, here you can see a little bit stuff with the numerics. There's no casting between a numeric and the big uint data type that comes out of that crate. So what you have to do is actually pull it out as a string and then push it back in so this way it gets converted in. But you're only doing that on the input and output. You're really working with the things as a big uint. So just to make sure that I got the code exactly right, where everything just worked, right? I said compare the fib PLPG SQL to the fib PL Rust, right? And it got back true. So they're returning back the same answers. If you notice there, trying to get the Fibonacci of 627,177. Very precise number, on purpose, because if I try to do one bigger, it's too big for a numeric data type. And going back, a numeric data type has 131,000 digits. So the result of this, if you're going to run it in PSQL, it's like pages of numbers. Really, really big numbers. So what did we get out of this? Run this in the PLPG SQL, got a really respectable number of a minute, 61 seconds. Returning that Fibonacci for that one is pretty decent. What's the guess on how fast it runs in PL Rust? 1 second. Right? So depending on what you're trying to do inside of the code, when you're able to do everything all natively in Rust and you're doing computations and other things, you can get tremendous performance gains. But if it's not the right fit, like things like SPI, you see things significantly slower. So with that, again, I'm going to take questions in the back, so this way the next speaker could set up. But thank you.